Hi everyone, welcome to Bordo's Forum. My name is Anup Bhalla and I'm going to introduce some of the latest products from United Silicon Carbide. United Silicon Carbide is known for its silicon carbide JFET technology. Silicon carbide JFETs are very robust devices which allow you to get the lowest on resistance for a unit chip area. And when you place a low voltage MOSFET on top of this type of JFET, you can go from what is a normally on device to a normally off device, and you can cover a wide range of applications. The silicon FET is custom designed for the cascode, usually adds about 10% to the on resistance because the two devices are in series, but it brings a great many benefits. The most important of which is it makes the device compatible with a standard gate drive. The FET has a 5-volt threshold, so you can usually use the device with a 0 to 12-volt gate drive. It also results in the net cascode structure having an excellent body diode with a low forward voltage drop of about 1.5 volts and very low QRR. So with these properties, it's clear that the device would be useful in a wide range of power conversion applications. And with the kind of low RDS-ons that we can now make, they're also useful in traction applications. So you can see we've listed here the focus area for silicon carbide FETs, which is onboard chargers and DC-DC converters in cars, and now traction inverters using our very low on resistance devices. The same properties make the devices useful in the battery charging area, IT infrastructure, and renewable segment. But JFETs are uniquely suited for the circuit protection area. This is an emerging area where if you need a normally on device, you can use the JFETs directly. If you need normally off devices, the stack cascode SiC FETs are excellent for this. The threshold of this device, JFET device, doesn't decrease with temperature, which makes it really useful in linear mode applications and all these circuit protection applications and for current limiting type of work. If you choose to use the devices in such a way that you drive the JFET with a milliamp of current in the on state, you can use the junction drop of the JFET to essentially sense the instantaneous temperature of the device. And this can be very useful if your goal is to develop products that can monitor their own health. So I said before, the reason we've chosen JFET technology is we can make the lowest on resistance in a given chip area. And we've used that property to release a 7 milliohm 650 volt and a 9 milliohm 1200 volt device, which are by far the lowest on resistance devices in the industry. Now these low RDS-on devices also have very good switching losses, so it makes them great for traction inverters. Here is an example of a 200 kilowatt traction inverter built by AC Propulsion using our 9 milliohm 1200 volt devices, SiC FETs, in TO to 47 4-leaded packages. And you can see they've achieved a pretty low cost inverter with very high performance, high efficiency across the entire drive cycle. Next, let's touch upon our next generation technology. That is Gen 4, and it's due for release later this summer. The radar chart there shows that we have taken the 650 volt rating up to 750 volt to accommodate 500 volt bus applications, and the RDSA of the technology is dropped in half. However, the chips have not really been shrunk altogether in half. The bottom of the table shows the chips are typically 65% of the old ones in size. When the chips get smaller, the capacitances get lower. This is very beneficial to reduce the QRR, and it impacts the switching losses, especially the E-on. So the switching losses are quite a lot lower. The structures have been optimized to offer very long short circuit withstand times up to 8 microseconds, and this makes them easier to use with standard gate drivers. This table here shows you some typical data on short circuit at room temperature and with TJ start of 175C. So these devices can be seen to pass 7 microseconds of short circuit at 175C with a 400 volt bus. The reason they can do that is visible from the short circuit waveform. As the JFETs self-heat, the current comes down. They tend to limit how much power gets dissipated in the device by themselves, and therefore they can withstand the short circuit for longer. And because the current is controlled by the JFET, it doesn't have a gate oxide or other things to degrade, you can have repetitive short circuit with no change in device characteristics. Thank you for listening.